And Paul, I just mentioned this last summer, so this is still relevant to this to CFRG, but all right. And the main topic today is going to be again about elliptic curves, and then we'll have some invited presentation. We'll review some PAC-related work and other topics. Okay. Adam? You're next, right? You're next.
Can you use a clicker or do I do it?
You say next slide.
You just say next.
All right. Hello all, Adam Langley, editing the CFRG curves document. I hope you can appreciate the curves on these slides. Okay. So I kicked out -02 yesterday perhaps, which is just like the current snapshot from GitHub as I had it. The main change recently is that Goldilocks has been added. The working group decided that 448-bit curve was going to be our high-level curve, which is essentially Goldilocks. Mike Hamburg has calculated the isogeny and the isomorphism steps to get to a Montgomery curve, so that you can use exactly the same Montgomery ladder algorithm with what is being called in this draft curve 448 now, to go with curve 25519. That should all be in there. Some of the algorithms had explicit, 255-bit numbers from curve 25519. Those have just been generalized to say like num bits or num bits -1, so that everything just works. I have not actually sort of rerun the algorithms to check the test vectors and such yet, but will do. Next slide, please. So the working group decided that the wire format for Diffie-Hellman would be sending the U value, which the draft already had, so no changes there. Next slide. The draft has been changed to say that you must check the output of Diffie-Hellman to see if it is the all-zero value. The background here is that these curves have cofactors of 4 or 8, so there are certain input points which you can throw at the other side, and you can guarantee that they're going to be tracked in this small group, and due to the way the curve is constructed, they're going to end up with the 0 value. For most protocols, this is not a problem. However, it has been a problem in the past for TLS, triple handshake. And so, anyway, I have changed this now to say you must check it is 0 and reject the handshake if somebody threw you one of these small order curves, small order points. So the parameter generation originally was taken from Microsoft's draft, and it has now been completely replaced. So we used to generate twisted or untwisted Edwards curves depending on the modular of the prime. Modular of the prime mod 4. And then once we got these Edward curves, we would do isogeny and isomorphism hops to reach the point where we actually wanted, i.e. curve 25519 or the other Montgomery one. We now, rather than start with Edwards at the top and go down, we now directly generate the Montgomery curves at the bottom. So we generate curve 25519 directly, and we generate curve 448 directly. And then if there is future signature work, then we can do the isogeny or isomorphism hop up to an Edwards or twisted Edwards curves as necessary. The parameter generation has also been changed from being pseudocode to being sage code, which you can run. And I have run it to check that, in fact, curve 25519 and 448 do pop out. Somebody on the mailing list this morning says you should also add the sage code to check the MOV degree and the CM discriminant and so on and so forth. And they are correct, although it might take me some little time to work through and figure out what that code will be. Next slide, please. Oh, so this is what I just said. Base points. So we had a base point generation algorithm when we inherited it from the Microsoft draft. It didn't actually generate the base points we were using, so I got rid of it. But now there was an open question about when we imported Goldilocks, what should its base point be? So we have, again, a base point generation algorithm which simply says it is the smallest U value which gives you a point in the correct subgroup. That generates the usual base point for curve 25519, and for curve 448 we end up with u equals 5. So there we go, that's now our base point, and we have an algorithm in Sage. Next slide please, or maybe that's the end. That's the end, right, that's it. Any questions? Excellent. I shall leave more time for the, I'm sure, fruitful discussion.
All right.
Thanks, Adam.
Right on time.
Do the next slide. Sure.
When you say abracadabra.
Okay, thank you, Adam. So I'm Kenny Patterson. I'm co-chair of CFRG. And what I'm going to do in the next 5 minutes is give you an update of where we've been and I think where we're going next with this curves activity. Next slide, please. So as Adam said, the group has finally selected 2 curves, one of which is curve 25519, which is already deployed in many places, and the other is colloquially known as the Goldilocks curve. It's called curve 448 in the current version of the draft, and this curve offers a good performance trade-off, performance security trade-off at higher security level. And the security level here is approximately 224 bits. There was a lot of discussion on the mailing list about whether we should, exactly which security level we should target and how we should trade off security performance, and this is where the list ended up. As Adam also said, these curves and base points are produced by a deterministic procedure that takes as its only input a prime, which defines the underlying field over which the curve is going to be defined. And in this sense, this determinism gives us a fair degree of rigidity, which speaks to this question of whether the curve generation process can be manipulated or not. I assure you it was not manipulated, at least not by me. Next slide, please. As Adam just said too, we have now almost finished defining how to do Diffie-Hellman key exchange for both of the curves. You can read about that in the draft. There's a little bit of detail missing for Goldilocks, which will be filled in pretty soon. And even the endiness question poll looks like it's going to end in a consensus quite soon. So we're even making progress on the endiness question. Next curve, next slide. Thank you. Other things that we've been doing as chairs of the work of the research group. So we have submitted, along with health and security aid directors, a short proposal to the forthcoming NIST workshop on curves. They're starting up a much larger activity, revisiting their standards for elliptic curves, and we're going to get involved in that as best we can. We've also had some liaison with W3C. They had some deadlines for new curves for their work, and we managed to, I think, get something that was useful for them. Perhaps somebody is here from W3C who can comment on that later. I'd like to also say that the mood of the mailing list has improved significantly, and yeah, it's easy to laugh when you're not actually trying to manage that. When you're trying to manage it, it feels kind of different. So we actually need people's help to continue to keep the mood of the list productive and respectful, and I think we're managing that quite well at the moment. So thank you to everybody for keeping it technical and restrained. Next slide, please. Okay, so where are we going next? This is the new part of the talk, really. So the next major work item, and actually the last major work item as far as the chairs are concerned, is to select and define a signature scheme for use with the new curves. We could actually stop right now and deliver to the TLS working group what we have without having signatures, because of course there are already lots of signature schemes that are standardized for use in TLS. You can use RSA PKCS if you don't care about security. You can use RSA PSS if you do, and you can even use ECDSA. However, the feeling here is that we can get significant performance and security gains, particularly implementation security gains, potentially by adopting a different signature scheme. So we want to put some time into arguing with each other about what is the right security scheme to recommend to TLS. Next slide, please. So I wanted to start the discussion here. There's already been some discussion on the mailing list about which signature scheme to use, but I thought it might be useful here to start the discussion by laying out what some of the options are for signature schemes. And I want to emphasize that what I've put here is illustrative and not definitive, and this is no way an endorsement from the chairs for any particular signature scheme or any particular approach. It's just some of the things that are in the air. Okay, so in other words, don't shoot me. Okay, so you could do ECDSA on an Edwards form version of one of the two new curves that we've standardized. Adam's already intimated that we'll be able to easily add Edwards form versions of the curves to the draft. A question for people here, would doing that be compliant with the NIST standard for ECDSA? Or does the NIST standard require you to use Weierstrass form curves? I don't know the answer to that question. There's been some debate about that on the list. A related question is, does that really matter? Do we care, does CFRG care about NIST compliance, and does TLS care about NIST compliance? You could do de-randomized ECDSA. So one of the really egregious problems with ECDSA is that it fails very badly when the randomness goes wrong. If you ever use the same random value twice when creating two signatures on different messages, you leak the private signing key, and all security is lost. So this is a common failure mode for ECDSA, and actually it's rather easy to avoid, at least in principle, by generating the random value R instead of using a PRNG or a true randomness source, by hashing together the message and the private key. Or potentially by applying a PRF to the message using a separate key K, a symmetric key K, which then becomes part of your private key. So you have to augment your private key in that case. Next slide, please. A third option is to use the ED-DSA signature scheme. This was developed by, gosh, a bunch of people. I guess the B is for Bernstein, the L is for Lange. The other ones I can't remember right now, so apologies if anybody's here from that set of authors. This is instead of, it's not a DSA-like signature scheme, it's more like a Schnorr signature scheme. This combines the de-randomization trick and a different verification equation. It has some computational advantages because it avoids an inversion during signing, and this is actually already deployed in OpenSSH, so it's got some, there's some kind of usage experience out there in the real world. And I mentioned the question mark others, because there might be other things that people here want to consider. Next slide, please. Okay, so here are some questions maybe to get some of the discussion going here. For the really technically minded people here, what other signature schemes should we be considering? For the people who care about NIST, does NIST compliance matter for TLS? How much might it matter for other applications of curves coming out of IRTF, IETF? And a slightly more kind of meta question. So the chairs have put a lot of effort recently into choosing very carefully questions which help to move the discussion forward, and running polls on the mailing list to try to really steer the group, not in any kind of calculated way, but to try and get the group towards making decisions about what we want to do. And the question then arises, how can we continue that process for signatures? If we just send an email to the list saying, as chairs, what's the right signature scheme, we'll have 3 months of violent disagreement on the list, and we don't really want to go down that route again. So any suggestions or help from the floor here about how we can structure the set of questions that we need to ask in this domain would be very helpful. And I think that's it from me. Is there a next slide?
Nope.
Nope. Okay, good. So I guess at that point I'll hand it over to the floor for comments and questions. And please state your name before you ask your question. Thanks.
René Struik. I just have a remark on slide number -2. I think this de-randomized ECDSA already exists for a long time as an RFC, right? So
Yeah.
I think there's nothing new here and nothing to be discussed in the CFRG for that. The other question I have is...
I disagree. Can I speak to that? I mean, there's,
sure.
there's more than one way of de-randomizing ECDSA, as I've mentioned already on the slide. So I think the RFC does it one way, but there's at least 2 ways of doing it. And I think ED-DSA does it a different way, potentially, from the RFC.
Yeah, but that's slide number 3, right?
Sure, but I'm saying that there's already deployed practice doing it a different way.
Okay.
Okay?
Okay, I just want to point out that's existing material, so it's not a new problem.
That's
but, the question I have is because it was raised at a very distant point in the past in this group that we would run with special primes for curve generation, right? So basically, the prime would be to the power n minus epsilon, right? So the curves that are currently picked, well, at least curve 25519 is an example because the offset is essentially 19, right?
Mm-hmm.
At the time, I think the co-chairs mentioned that there would be another process coming down the road where we would consider potentially non-special form primes, right? So I'm kind of curious about whether we want to go that route, or I want us first to finish work, of course, and not have another red hole opening up.
I think you're just generating one now, aren't you? You're by asking the question now. You're generating that.
But I think to be fair to the people who had concerns about special form primes, I think there should be some assessment of how do we go about people who have those concerns. I'm one of them, actually.
Okay, so let me just speak briefly to that comment or question. I mean, absolutely, if there's still energy in the group once all of this work is done, to come back and look at general primes or non-special form primes, absolutely we should do that. And I hope that the people who want that for their products and systems will come forward and make it happen. But right now, we're focused on signatures.
Okay, Joavnir, about these questions about NIST, the only thing anybody is ever sure that is going to be NIST approved, FIPS approved, is ECDSA, regular ECDSA on P256. Anything we generate here is maybe going to be acceptable, maybe not. So I don't think that has to play at all in our considerations. Okay. We should just do what we think is best.
Thank you.
Joe Salloway. Just to echo what Yoav said, yeah, NIST compliance is important, but we have that in P256, and anything else would be speculation and what happens. And maybe that will work out, and maybe it doesn't, but we already have something that is NIST compliant.
Good.
Philip Pound-Baker. On the de-randomized whatever bit, we have a very similar situation with defective keys that come from not enough randomness. And one of the things that I've been looking at has been the difference between telling somebody how to do something correctly and being able to know whether or not they have done that. And that came up very much with the Netscape randomness flaw, in that I'd actually told them 18 months before they got broken that they had a problem. And so with these mechanisms for making ECDSA, whatever, secure, is it possible for somebody to tell whether the black box is doing the right thing or not in any of these schemes? And if there was, that would be the one that I would want to go for. If there's a way of auditing and finding out whether the thing does the right thing or not.
So one thing you can do is okay, so the generation of the pseudo-random value instead of the random value still involves some secret information, either the secret signing key or a separate PRF key. And that makes it not possible to publicly test for somebody who is not a key holder whether the system is working correctly. Okay, and that's with good reason. You need this randomness still to be private.
Well,
or the pseudo-random value to be private. However, you can generate test vectors.
Yes. I understand the problem as it's been set. I'm just wondering if there was a way that we can maybe find a way around it.
Okay, I don't think so.
Paul Hoffman, echoing what was said before, but I think it's actually worth it because there were a number of people on the mailing list who really were like, oh, you know, has to be FIPS compliant and such like that. The IETF has actually had a history of doing things where NIST told us, sorry, now that you've done it, it is now no longer compliant, and we sort of had to browbeat them into changing that. So just to make it really clear, even if NIST says now, yes, that will be acceptable, they could change their mind later and such. So it really should not be part of our consideration. And at the same time, we, for some value, we should engage with NIST so that as soon as we have something for real, they have as much chance as possible to do the same thing.
Mm-hmm. Thank you, Paul. I think we should make that value of we, everybody in this room who cares about the next generation of elliptic curve cryptography. Because the NIST is starting up this process which potentially puts everything back on the table again in terms of all of the curves and algorithms that they're going to use or standardize for elliptic curve cryptography. So we all need to get there to Gaithersburg and bang on the door. Right. Exactly.
Yeah. Mike St. John's. One of the things I noticed when I was looking at this stuff is that X9.62 and X9.63, which are all fed into the NIST process, have about 30 or 40 organizations that are very related to financial security. We may want to think about not so much NIST, but what this is going to do with respect to the banking, value and money, and whether or not it's going to be acceptable to the conservative bankers of the world.
Okay. Do you have any suggestions for concrete mechanisms for reaching out to those folks?
It's ANSI, I believe. So we've done code things with ANSI before. It may be worthwhile to get the X9 folks to basically come in for CFRG at some point along the way and say, how do we make this work and make you guys comfortable?
Yep, great idea, thanks. Any more? Come on, there must be more. It's Olympic curse, for God's sake. Hey.
Yeah, Andre Girso.
Andre.
I wonder if this is a final decision regarding unified formats, so ECDH keys used with signatures and vice versa, and compressed versus uncompressed.
Okay, so I can speak to the fact that for Diffie-Hellman, the view on the list, and I can't remember the exact score in terms of votes, but the rough consensus on the list, I think I can go that far, was to go for U-coordinate only for Diffie-Hellman, which implies that issue at least is settled.
Is there a plan to reach out, for wider audience, perhaps? Because, once it's decided, that's forever. And, one view is that CFRG probably maybe shouldn't define it exactly what it should be and to leave it to the high-level protocols. So in a way, there's a way for CFRG to say it's XY, kind of kick the can down the road and let individual groups decide.
And security area director is going to jump on you. He's behind you.
Look out behind you.
It's probably obvious, but please don't give me options to the higher level protocols unless it's absolutely necessary. So no gratuitous options, please. And by the way, I think there are other IETF users that also want signatures beyond TLS.
Mm-hmm.
Okay.
As long as you can make it for me, please.
Tanya, will you come into the mic?
Given that there are arguments, Daniel Kahn-Gilmore. Given that there are pretty common conventions that we should not be reusing keys across purposes, I just wanted to say that it seems like trying to make sure that we have the same format for DH keys as well as ECD, as well as whatever signature scheme we come up with, doesn't make sense to me. And if the shorter keys have a consensus on the list for DH, and they actually are protective for DH in some cases, we should go with those, and we'll deal with the signature formats when we get to those.
I just put my vote in for as small as possible, for as strong as possible, because I work with vendors that count bits in the air and bits in memory. So keep it small, please. It's small. What? Bob Moskowitz, HD Consulting. Thank you. So I'll just put my +1 for it. Keep it small.
Thank you. Adam Knightley, Google. So I would suggest as a way to move forward, there seems to be quite a strong feeling in the room that we should not worry too much about NIST, but it would be good to confirm that on the list and do a poll saying, does our signature scheme have to be sort of exactly ECDSA? Because if yes, then that's answered. But assuming we get a no, my next suggested poll would be, does it need to be randomized or can it be deterministic? And then after that, I think we poll probably on compressed points, compressed coordinates, and then perhaps something about how Schnorrish should it be. And I think that by the time by the time we've got answers to those 4 questions, the first one of which provides very little information, I think we'll be in a pretty good spot to throw a dart and hit something reasonable.
Thank you. Oh. Stephen, get ready.
Andrew, just quickly to address some comments.
Sure.
I think there's a benefit in the unified point. So, one of my preference for that format I propose is unified. You can still not share keys if you want to. And the benefits would be same test vectors, the same representation, sort of deviation from what we have right now, where you have points represented in different way depending on its encryption key or signing key. I think it would simplify a lot of things.
Adam Langley, Google. So we are, I don't think we are in fact giving up the possibility of unified points at this time, because we can still choose to use the trick named after you, where we only have to sort of express the U value, right? And so it is possible that a future signature scheme could use these same point formats as we have, I believe, decided for Diffie-Hellman.
It's important to
yes.
Yeah, come to the mic if you
So,
want.
I mean, the point he was making is it's important to think about now because, yes, I don't know, the chairs will decide whether or not that question is still open.
I mean, I think to answer the point, we did think about it on the list at the point when we were discussing which format to choose for Diffie-Hellman. I think people who were discussing that were aware that it had wider implications than just the choice for Diffie-Hellman. I feel that people were quite well informed at the point when they were discussing it. Somebody's going to come and contradict me now.
Can I just jump on that for a sec?
You better state your name.
I think one of the
Can
points...
you state your name?
Oh, sorry, René Struijstil. I think one of the confusion points that was raised on the list was that affine point representation would not be possible in an effective way using Montgomery multiplication. And it turns out that the incremental computational cost in generating an affine representation is virtually zero. And if you want, I did calculation independently of n-ray, and we came to the same conclusion, and we can share it.
You have to bring those things to the list in a timely fashion when the issue is being discussed. Otherwise, that information is not available to the list.
Rich Salzak, it's done. We made the decision. I think the people who made it were as informed as they could be at the time, and it's now time to just move on to the next argument.
Thank you.
So, Stephen Pearl. So on the kind of your last bullet or meta point about how to progress, so you only mentioned one of the, there's a bunch of possible ways that the signature work might go. There was only for one of them that you mentioned that there was any kind of notable implementation.
Yeah.
At that point, it might be worth, rather than doing the polls on the list bit by bit, it might be worth, even in the room here, saying, is there support for that particular thing already? And then you could maybe short circuit some stuff. And if there's not, then I think, the process Adam suggested sounds good.
I mean, that's an interesting idea. I think this incremental approach that we've been following in the last few months has been quite successful for us in reducing the potential for controversy. And so, respectfully, I think I'd rather stick to the kind of approach that Adam suggested of going step by step. But if people want to come up to the mic now and say, I love EdDSA, they're more than welcome. I mean, that's an absolutely fine thing to come and do.
Adam Langley, Google. So one of the concerns with EdDSA right now is that you have to hash the message twice. You can't. So the APIs currently, you have the message incrementally. It doesn't let you do that. I'm trying to talk to both Steve and the mic. All right, I'll talk to the mic. Imagine I'm making eye contact and not being socially awkward. So EdDSA hashes the message twice, so you have to present the whole message to it in one go, which is different from many current APIs where you can sort of incrementally add the message along and then say, I'm done. How important that is, I don't know, but it's a more sort of complicated question than just like, should we do EdDSA?
I understand.
Okay, any last thoughts or comments or questions? If not, then I guess we can move on to the next agenda item. Thank you.
Next is script.
Okay, I'm here presenting for Joseph. keep stepping up. I'm too short. Okay, is that better? I'm sorry, that's sorry. Yeah. Which way does the script go? Okay, so Simon seems to be a tear of taking all these existing deployed on the internet standards and or de facto standards and writing them out so the IETF has a touch point to make the reference, and this is yet another one of them. script, it's a key derivation function. It's based on a password. It's pretty widely used. Facebook, Android uses it now. Litecoin. Apparently, you can now find ASIC Bitcoin miners that know this, know the algorithm. It is going to appear in OpenSSL 1.1, maybe plus or minus. Next page. The current draft has pseudocode, it's actual real code in Python. It includes test vectors, and it has been used to drive implementations, notably the aforementioned OpenSSL. Next. The goals of the document, this is not intended to be a CFRG document. It's going to be an individual submission, informational, so that anybody else who wants to use it has test vectors, sample code, so on, so they can interoperate with those little things like Android and Facebook and so on. And that's it. Any questions?
Ben Kaduk, so just with the intended status of informational, and you mentioned that you could replace PBKDF2 in some uses, so like if we wanted to make a new Kerberos encryption type that used scrypt instead of PBKDF2, there's a little bit more administrative hoops to jump through to use that as a normative reference if it's information.
True.
Adam Langley, Google. So is this better as a historical RFC? Because by the time that OpenSSL 1.1 comes out, the password hashing competition might have concluded, right? I'm not sure when it's scheduled to, but OpenSSL 1.1 is probably quite some time away.
Sure. So you want to talk about historical? Should we talk about Android 2.2?
I don't know why that was a dig at me. I never worked on that, but.
Information. It's not on the standards track. It's just information. If you need to operate with these things now or then, or you're running OpenSSL master or whatever, or Libra. I mean, it's just the code's out there. The main point is to show that it can be done to drive an implementation. That's all.
Okay. Maybe I can just interject as chair at the moment for a second. There is this password hashing competition that you mentioned going on, and I think it would be quite good for CFRG somewhere down the track to take a look at its outputs and maybe see if we want to think about adopting any of those as CFRG standards or documents or whatever. And having a wider look at the whole area of password hashing would be something for us to do once we're done with elliptic curves, though.
Does anyone offhand know when the password hashing competition is scheduled to conclude?
I think they're in their final stage now. They've got a list of so many finalists which they're evaluating. So I would guess another 6 to 9 months.
Okay.
Channeling Nico from the Jabber Room. Why informational? If you make it informational, then standards track docs will have a hard time using it. I'm just a messenger.
Nico knows that.
Yeah, it's not, not true.
Okay.
Thank you, Rich.
Here. I'll be break eraser.
I'm good on time.
Yeah, I think we're fine. Worksheet slightly ahead of.
We had.
We're doing okay for time.
Yeah.
Okay, so Paul
20 minutes ahead.
Closer to the mic. I can take it with me. Like a t-shirt. Well, I'm actually used to speaking at mathematics conferences and not CS conferences, so this is the first of many social faux pas I'm going to commit, but I feel like I'm on Dr. Phil or something. But. Okay, so anyway, next slide. So the reference for this is this paper by Angela Goldfeld and Mu from 2006, and this is a asymmetric key agreement protocol, and the emphasis of this protocol is for low-cost platforms with very limited resources, so not PCs, not smartphones, but tags, essentially. So RFID and Bluetooth and tags using NFC. In other words, small tags you want to be maybe thinking about using in the Internet of Things. And the important thing about it is that the complexity of the operation to do key exchange scales linearly with the security level, unlike RSA and ECC. Okay, next. So here's a comparison of this with ECC. So we have ECC 283 on the left at 128 bits of security. And the implementation for the ECC is taken from this paper here, measuring clock cycles and gate speed in a hardware implementation. And as you can see, there's quite a big performance gain. So weighted performance here is clock cycles times gates. And as you see, as you go down the column, they try to cut the clock cycles by increasing gates. You still have a big win on the other side. So next. Okay, so it's a Diffie-Hellman scheme based in a non-abelian group, unlike the things you guys are used to. So like Z mod n times or elliptic curve. So the underlying algebra comes from n by n matrices over a finite field and uses the braid group as the non-abelian part, the essential non-abelian part. Private keys look like a pair of, I'm going to say a little more about what that looks like in a second. So the private keys in the exchange are a pair of a matrix and a braid over this field. Public keys are a pair of a matrix and a permutation on the same number of letters as the order of the matrices. And each user also knows a fixed ordered list of elements in the finite field. And after they've computed doing the key exchange and the shared secret, it looks the same kind of data as the public key. So essentially this is a matrix over a finite field and a permutation. Okay, next. All right, so the security level, of course, depends on the parameters, in particular on n and q. N is the size of the matrices and the number of strands in the braids. Q is the finite field, and the lengths of the braids. And it scales linearly with the lengths of the braids. So this is where the linearity comes in. The maximum security level that can be attained with this particular set of parameters is n times log of q, not log of q over 2 like in ECC. So what this means in particular is that because you have this factor of n, you can use moderate-sized finite fields, and that's an important part of the fact that it can be used in these low-power environments. I mean, you don't need to use multi-precision finite fields to do computations. You can, in best cases, you can even use lookup tables for small finite fields if you have enough memory around. The computational problem that underlies the public key part of it is taking place in the braid group, and it's called the simultaneous conjugacy separation search problem. So there have been other schemes that go into the rubric of braid group cryptography that were introduced before this, maybe in the late 90s, early 2000s, and that's a different computational problem. That computational problem is the conjugator search problem, and that has had a lot of work done on it, a lot of work looked at it, though there's still plenty of things we don't know about it. But this is not the same problem. This is a completely different problem. And any attacks done in that problem have nothing to do with this problem. It's completely different. Okay, next. I think, did we go too far? Or? Yeah, okay. Okay, good. So if you've never seen a braid before, if you don't have young daughters, for example, like I do, or young hippies in your house, so there's a braid. So it's a collection of strands. You have the braid group of order n involves n strands. As you progress from left to right, they become entangled, flip around each other. And the braid keeps track of that progression of flips of strands. So if you notice, if you go from left to right, you get a permutation. If you label each braid by some number, you get a permutation on that set. But this is recording more of that because it's recording the trajectory as you go from left to right. But there are equivalence relations that basically come from the topology of the braid group, underlying the braid group, which say when two of these expressions are going to be the same. So like in this example down here, you can see at the very end, you've got the third strand crossing over the fourth one and then back up, and that's obviously not doing anything to tangle the strands up, so that's a relation in the expression. So this expression on the bottom, encoding this braid, is equivalent to several others, in fact, infinitely many others. And a very difficult problem in the braid group is determining given a braid encoded in this way, the minimal possible expression for it. That's a very difficult problem. Okay? Okay, and another essential part of this also is a certain action of the braid group on the matrices. So each simple twist in the braid determines a sparse matrix in by n, which we call a colored plurality. How much time do I have, actually?
Yeah, well, way ahead.
Do I have more? How much? Can you guys tell me how much time I have, or?
You're all right.
I'm all right? Okay. I'm not sure what that means, but keep going. Okay, so we have each generator, each simple flip determines an n by n sparse matrix, and that the sparsity is also important for the ability to run in these low power environments, called a colored Burel matrix. The matrix depends on this fixed set of elements in FQ, but as you move down the braid, as you apply the braid to the matrix, that correspondence between generators and elements of FQ changes. So it's not fixed at the beginning, so changing the braid changes it as it moves down. And that's really the eraser part of the name. That's, as you move down, there is this representation of the braid group on the matrix group is being masked as you move down the braid, and it changes based on which braid you have. And using this is how the public keys are produced from the private data. So you should think about this computation on the bottom as being like the first exponentiation in Diffie-Hellman. So you Alice applies her braid to her matrix, Bob applies his braid to his matrix, and get the public key. Okay? Next. And they take their public keys, and they multiply their private matrices to construct the shared secret. First, they do the ordinary matrix multiplication of their private matrices against the matrices in the public keys, and then they multiply. They apply their private braids to the results of that multiplication. And then, if everything's set up correctly, of course, you guys are spending apparently a lot of time on mailing list discussing setting things up properly. You know that it's a non-trivial problem, but I'm just not telling you how to do it in this short time. The secrets agree. Okay? I think that's it. Thank you.
So questions for Paul?
I still have to say name, René Struik. Just a question. I looked at your scheme a few years ago, and
Yep.
I was wondering whether you also have an accompanying signature scheme.
Would you like to answer that, Derek? Or?
Hi, Derek Atkins. We do. It uses a different set of hard problems than this one, and we're still actually fleshing it out. But there is a signature scheme. I can't talk yet about how reasonable it's going to be, but it does exist.
I'll ask the same question I asked on the list. So why are you presenting this as something specifically for IoT? Yes, I understand that maybe the big ECDSA or ECDH is not suitable for IoT, but why can't we get like the 90 times performance in regular servers by using this instead of what we're using today?
Well, it's all a matter of what you want to put in your toaster to make it a smart toaster, right? It depends on what resources you have available to you. If you have sufficient resources to do something else, then do something else, right? Is that what you're asking? Or?
No, I can get, if this is truly 90 times faster than ECDH, then I can get 90 times more sessions from my server than I could without this.
Yep.
So why aren't you pushing this as something for the entire internet versus only for IoT?
Well, I'm not here to push anything on you. Again, this is maybe a cultural difference. Mathematics conference versus a CS conference. But
what are the downsides of using that as opposed to ECDH?
I'll let Derek answer it.
So again, Derek Atkins. We've been focused on IoT only because ECC has a lot of history and implementation experience and deployment experience already. So trying to get that displaced is a lot more effort than going after a market that's not being served. So that's why, as a company, SecureRF is focused on the area that's not being served by ECDH. Now, it doesn't say we can't be using it there, and one of the reasons that we're bringing it here is that we're trying to come up higher in the stack. So that's why we want people to look at it. But again, we're as a company, we're focusing on the stuff that's not being served by Without.
I understand, but this working group specifically is spending a lot of cycles on replacing the current status quo with something that's apparently much slower than what you're proposing.
Yes, it is.
Channeling Nico, in response to Yoav, Nico's saying there's a trusted third party that can totally break the system, so you don't want to use this outside your personal set of devices.
So again, Derek Atkins, that trusted third party is only used to effectively set up the conjugates that get used to create all the public and private keys. So if you truly have a trusted third party, as soon as you throw away that private conjugator that's used to generate the conjugates, then no one can break any of the system. So it's basically you create a random braid, and then you create a bunch of conjugates from that. And as soon as you throw away that conjugator, then it's just all public information.
So Kenny Patterson here, so you're saying there is a backdoor in your system?
No. Because the code is written to throw it away. So it's that, and the code can be audited and say, oh, throw it away.
Is that the answer to Nicholas? Who would you trust to throw away the conjugator?
I trust me.
So Kenny Patterson again. So I actually had the pleasure of reading your research paper this morning, or at least skim reading it. And I noticed that you had rather optimistically assumed that the best attack against your system, and maybe it is the best attack that exists today, is an exhaustive search for the key. And then that's where you get this n-log q estimate for the key size, where, as you say, elliptic curve cryptography needs keys that are twice as big, and therefore everything's twice as long. So I assume that if this is subjected to a more extensive cryptanalysis than already has been applied to it, then you might find that it's not quite as efficient after all. Does that seem like a reasonable way of thinking? I mean, that's the sort of history of these kinds of alternative public.
Yeah, I mean, that's a general principle, right? It's not. But I would say this: so there's exhaustive search, and stating a security level that's what that means. But there are other attacks. There are two other attacks. One is a attack to try to recover this conjugator that Derek was talking about. Another attack is to try to recover the matrix part of the first private key. We call the first private key the matrix part of the private key, and that's like a replay attack. So both of those have been refuted in that as soon as the parameters are sufficiently big, they completely disappear. They reduce to exhaustive search. So yes, I mean, if it's like factoring numbers. I mean, if the numbers are too small, then I can factor them. But if they're big, then you can't. So somewhere in the middle is where you want to be, and that's the same thing. So.
Yeah. So maybe putting it a slightly different way, I think the way your research paper is written led me to believe that you thought the only possible attack was an exhaustive search, and that's.
Which paper are you talking about?
The one that's on your current company's website that was linked to.
Does it have my name as an author on the paper, or? It's probably I think it's probably the first paper I referenced.
Okay.
So at that time, that was 2006. There were no other attacks on the scheme at that time. And then these other two attacks came up. So.
Okay. Well, maybe we can discuss it later
Sure.
over coffee or something.
So going back to Nico and Yair, have you tried an optimized implementation on a commodity CPU? Is one of the reasons why this works so great in your target domain that you get to customize the hardware, whereas small finite field operations are not particularly well supported by common CPUs, therefore it would not be nearly as good over ECDH on them?
Well, I think, do you want to answer that? I'm not sure I understood the question. So you answer again. Ask it again.
Does this stuck on commodity CPUs because you need lots of operations on small finite fields which they basically don't support? Are you targeting these little IoT devices because you can then design the hardware and build in the finite field operations you need? Yes. Okay, so it would not be 70 times faster on a commodity CPU.
I've seen in some tests, and they're not exhaustive tests, I've seen about 50 to 100 times speed improvement on commodity hardware. But I haven't done exhaustive testing. I probably haven't done the most optimized ECC implementations, and I haven't used the most optimized in Harvard either. So I think it's still an improvement on hardware, and if you have more, you can get bigger fields as lookup tables, which helps speed up a lot as well. But we're as a company, we focused on a market that hasn't been served. So that's why we're focused on IoT, because it's not served by anything else. Just to summarize, it's not that we don't want it to be higher up in the stack, which is, it's already higher up in the stack is already served by existing.
Stephen Farrell, so I just want to get clear on the trusted third party aspect. It wasn't entirely clear to me. I mean, is what you're saying that you need a trusted third party for that can know the private parts of all of the relevant people who need to talk to each other?
No.
Okay, so can you maybe clarify that, because it's not clear to me.
So imagine if you needed a trusted third party to come up with an ECC curve. So just follow my logic. So imagine you had a trusted third party that you needed to generate an ECC curve. Once the curve is created, it works just like ECC today. However, you needed that trusted third party to actually generate the curve. So that's effectively what we have.
So then I think the answer to my question was yes.
No, because once you throw the
if I have a million people who want to be able to talk to each other and negotiate keys,
all you know is the curve.
So there needs to be a trusted third party who could possibly know all those million private keys.
No, the curve.
Yes. The curve is public, and you share that information publicly. There's no private. You don't need to go through the trusted third party to get your key material. The curve gets published. You can put it in the New York Times, public information, and you generate everything from it.
Adam Langley, Google. I think the answer to your problem is that if we were to do this on a large scale, you would need to build a multi-party computation to generate these parameters and have the US Air Force, Chinese government, Dan Gilmore, right, have a huge set of people, all of whom would need to collude in order to backdoor these things and generate the parameters that way.
Think of it like how the root zone key gets done.
I was thinking of the seeds for the NIST curves, actually.
Okay. Okay. Thank you.
Okay, thank you.
Thank you.
Sorry, one more comment from the room.
Okay. 2 more minutes and then we'll move on to the next topic.
So Nico again, there's no problem with this except that one has to generate one's own parameters, because there's always a backdoor that can only be closed by throwing away the secrets used to generate it. And so the only trusted third party one can trust for this are the trusted third parties one runs.
Is that from the Bible or something?
No, it's the equivalent of two can keep a secret if one is dead.
Okay, I can live with that.
Okay, thank you. Okay, next is hash-based signatures. Hello.
So we submitted a draft on hash-based signatures, which is called XMSS, Extended Hash-Based Signatures. Next. Okay.
Yes.
So brief reminder on hash-based signature schemes. They only require a secure hash function, so you don't have any number theoretic assumption like discrete log or RSA involved. The security is quite well understood. We've got security reductions, and for the hash functions, we've got kind of a good understanding now. They are post-quantum if you don't use a number theoretic hash function, and they are considerably fast even without hardware acceleration. Next. So the basic idea is you generate a set of one-time signature schemes, one-time signature key pairs, and then build a binary hash tree on top, and the root of the tree becomes your public key. And if you sign a message, you include the index of the used one-time signature key pair, the one-time public key, the one-time signature, and these red nodes, which are actually the nodes that the verifier needs to compute the path from the one-time public key to the root. Next. So there is a first draft by McGrew and Curcio, I think from last year, on hash-based signatures, which specify the scheme developed by Merkel in the 70s. Next. So why another internet draft? So the scheme that we specify makes weaker assumptions on the used hash function, which means we've got stronger security guarantees. So especially we do not require the used hash function to be collision resistant. That means also we do not have to deal with birthday attacks, and hence we get smaller signatures, like roughly a factor of 2. We can handle a virtually unlimited number of signatures per key pair. So as you generate a fixed set of one-time signatures, the number of signatures you can do with one key pair is limited. And we can increase this number up to 2 to the 60, for example, without any problem. And finally, we can decrease the key generation and signing times for the multi-tree version. Next. So in the draft, we specify a one-time signature scheme, a tree scheme based on that, and a multi-tree version of this tree-based scheme. So the one-time signature scheme is a Winternet's one-time signature scheme, which is conceptually the same as the one in David's draft, but this one has a little tweak that allows you to get away with, without relying on collision resistance. Next. So our general design choices in the draft, we only define public key and signature format and semantics and verification. We leave to the implementer how the secret key is implemented, in consequence also how the key generation works in detail. So we only specify how you compute a public key given a secret key. There are many trade-offs possible. We give examples how it can be done, but we do not give a mandatory way, and simply because it doesn't affect interoperability. And the same applies for signature generation, so we exactly specify what has to go into the signature, but not how it must be computed. One of the advantages is that this prepares for recent stateless hash-based signatures. So one of the efficient stateless schemes uses actually this multi-tree version as a subroutine. And I will not talk about signature and public key encodings because we follow the approach that McGrew and Curcio take. So the difference between our Winternets and the one used in the draft before is that it uses bit masks. So if a chain is computed before the hash function is applied, there's an XOR with a set of values which are in the public key. And this allows us a security reduction without collision resistance, and hence we get half the signature size. And there's a second Winternet's variant that achieves the same properties, but this one has the tighter security reduction and is easier to implement, so that's why we settled for that. Next. We describe the key generation and signing for a random secret key, so we simply assume we've got an array. It works for any pseudorandom key generation method. We give some security requirements that a method has to fulfill, and give one method that actually achieves this, but leave it to the implementer how to actually do it. The verification is described in 2 steps. There's one function that computes a public key from a signature and then an additional comparison. The reason is that XMSS only uses this function that computes the public key from the signature and delays the comparison to a later step. But we wanted to also allow the standalone usage of Winternets. Next. So for the tree-based scheme, the difference is compared to Merkel's initial scheme, so that's described in the previous draft. There are also bit masks used in the node computation within the tree. So there also happens an XOR before the hash function is applied. In addition, the leaves are not simply computed as a single hash of the public key, but they are computed as a binary tree with bit masks of the single public key elements. And the message digest uses some randomized hashing, actually a de-randomized hashing, so that's exactly the PRF version that we had for ECDSA in the discussion. And all this together allows you again to get away without collision resistance, so we've got a collision resilient scheme and half the signature size. Next. So the first point I already explained. So this WOTS PRF is this third variant. Then we describe the methods in terms of all the one-type signature key pairs stored. We give an example of a pseudo-random key generation method, but as for Winternitz, this doesn't affect interoperability, so we leave it also to the implementer to perhaps use a different method. The verification is split in a similar way this time. There's a function that allows you to compute the root from a signature, and then in comparison, and the reason here is again that this root from signature computation is required by the multi-tree scheme. We completely specify tree hash, which covers key generation and gives you one way to compute an authentication path. That's probably not what you want to do in practice. There are more efficient algorithms, and we have links in the draft, but we didn't intend to cover these algorithms because they also do not affect interoperability. Next. So this multi-tree version, that's what actually allows you to do a virtually unlimited number of signatures with one key pair. So the idea is to use multiple layers of trees, and you use the layer on a higher, the tree on a higher layer to sign the trees on the next lower layer, and the tree on the bottom layer is used to sign the actual messages. And then you can reduce the key generation time for a total tree height of h from 2 to the h to d times 2 to the h over d, where d is the number of layers. So from linear in the number of signatures that you can make to the d's root, roughly. And it also allows to reduce the worst case signing time from h over 2 to h over 2 times d. These require certain algorithms where we point to, but we do not describe how it is done in the draft. I think it will simply get too much in the draft then. Next. The first point is exactly the same as before, so we describe everything as if the XMSS keys were stored. At that point, we describe also a method or variants of sign and verify for XMSS where the initial message hash is omitted. And we made one design choice at that point, namely the tree height of all the internal trees, and the Winternitz parameter for all the trees is the same, because then we get an easier implementation. Next. Lastly, parameters. So we propose parameter sets for different settings. We try to cover 128-bit and 256-bit classical security, and also 128 bits and 256 bits quantum security. What I should mention here, so in the first case, we use AES 128 to implement the internal hash function. That's kind of easy because we have to deal with fixed length messages. We didn't want people to implement a full-fledged hash function out of AES, so we settled for the message hash for SHA-3 256 for these parameters. Next. For our parameters, we limited W to be 4, 8, or 16. The reason is, on the one hand, these are powers of 2, which allow for an easier implementation, and these values give you kind of the optimal trade-offs. So lower values are simply less efficient in terms of speed and size, and bigger values will not reduce your size, the signature size significantly, but you pay a lot in terms of speed. Then we limited the tree height for XMSS to 10, 16, and 20. This was kind of an arbitrary choice to get a bit of everything. Bigger than 20 is probably not so intelligent because the key generation simply gets too slow for a single tree. For the multi-tree setting, we restrict for the same reason the single tree height to be 5, 10, or 20, and then have support total tree heights of 20, 40, and 60. I think bigger than 60 doesn't make sense, so 2 to 60 signatures is already something probably even an SSL server will not do within 100 years. And less than 20 you wouldn't use several trees. Next. Now that gives many parameter sets. One question where we would ask for feedback is, are these too many? So we've got 27 parameter sets for XMSS. For the multi-tree version, 72. On the other hand, the second question for feedback would be, did we cover every scenario? So are there applications where someone would say, I would like other parameters? In addition, we specified 0 bit masks parameter, where these bit masks are simply set to 0. Then we can omit them in the public key, which gives us a very small public key, which is only 1 hash value. But we don't have this collision resilience property, so actually in that case we rely on the collision resistance of the hash function, and we end up with something very similar to the old draft. So the question is if this is really needed here. Next, there's no IPR so far on the topic as far as we know it, and there were old IPRs that run out. Yeah, next. So we get smaller signatures, faster signing key generation. We can do up to 2 to the 60 signatures per key pair with the parameters we propose. We get stronger security guarantees, and we prepare for stateless schemes. Next, or thanks.
Questions, comments?
Adam Knightley, Google. Going backwards through, as I remember, why can't you generate the bit masks using some stream cipher? Why does the public key have to expand so much to support them?
Because then you don't get provable, or you don't get the reductions going. It's actually a very annoying thing, but they have to be independent. So that's a question. That's simply our proof techniques that we know today.
Okay. If this is a stateful scheme, yes.
Yeah.
But surely the motivation here is conservatism, right? If you're building a signature scheme that really needs to work for a really long time and has very high security demands, surely that's contradictory with using a stateful scheme. I'm suggesting that the stateful scheme is very dangerous, because obviously if you ever sign something, forget your state and sign again, then you've gone horribly wrong. You've leaked too many Winternitz values at the bottom there, and so your whole scheme has exploded.
Definitely, you have to make sure for these schemes, and we comment also on this in the draft, that the state is always corrected. You have always to increase the index. You must not use one index twice. There are applications, for example on smart cards, where this is easily possible.
But if we're trying to pick up people who are extremely conservative and want to use this scheme with its great security properties, surely a stateful scheme just breaks all that, because this is like the ECDSA sudden death property, but worse. So I'm suggesting that you'll only pick up people who are really conservative, and those people will only go for a stateless scheme.
We've got some people that want to go for these stateful schemes. For certain applications like software updates and similar, this is definitely the easier way to do, because you get smaller signatures than for the stateless schemes. I mean, I'm one of the developers of the stateless scheme. So,
Yes. I'm suggesting that you should be standardizing that because that's way more useful.
One of the points is this is the first step towards standardizing the stateless schemes also. Because what we see here, is one of the main building blocks of the stateless scheme.
Sure.
And for certain applications, I would still consider these schemes because they are simply much more efficient. So we have signature sizes which are roughly 20 times those of these schemes for the stateless schemes, and these are already not the smallest signatures.
Are you planning on going forward and also specifying Sphinx or other stateless schemes using this as a good? Okay, thank you.
Hannes Phoenix, so you mentioned a couple of times the efficiency. Is there somewhere a place where you put some performance data for this?
There is performance data in the original publication, so we can, we've got an implementation available on my website, which is not optimized, it's simply proof of concept, but that's...
It's a PC-based implementation of what was it? Is a PC-based implementation of, because you mentioned smart cards previously, so
we've got a smart card implementation. We've got numbers out for this, but that code is sadly under NDA because of the smart card we did this with Infineon and they didn't want to give it out.
I see. Okay, I will check out your webpage.
All right, just do it like this. Okay.
Andreas Hülsing, it's in the program, I think.
Yeah. Thank you. Okay, what's next? Yeah, requirements.
Thank you. Next slide. I'm Dan Harkins. Next slide. Jorn and I are writing a requirements draft for password authenticated key exchanges, and basically the intent is to express the consensus of the research group when we get around to discussing these things. And as much as I hate the concept of requirements documents, it's probably a good idea in this case. We've already got 2 PAICs in the research group, and to keep the group from spinning out of control on this, what ends up being a controversial subject, we thought it would be nice to get some structure around this topic. Another reason we're doing this is because the chairman asked us to. It's being actively edited now, and we're hoping to have a 0.0 draft submitted real soon now. Next slide. So basically, it's just describing some of the different options you could have in a PAIC and the different features, so that when people start proposing their PAICs, they'll be able to refer back to what features their particular PAIC has. So it's basically talks, you can have an augmented PAIC or a balanced PAIC. You can encrypt public keys or not encrypt public keys, that sort of thing. And it has a list of, hopefully at this point, non-controversial requirements, and then when we get around to discussing it on a list, we can change them or add or subtract to the list. Next slide, please. So as an example, these are some of the requirements, and I don't want to discuss it here, but these are hopefully motherhood and apple pie kind of things. But then I guess the group will congeal around some additional requirements or change these if they like. So, coming soon to an inbox near you.
Chairs don't want actually to rat hole on the requirements at the moment. This is just sort of for your information. The draft is coming. When the draft comes out, then we'll discuss it there. But if there are any quick comments or questions. Okay, run away. Hello?
I'm Shin with AIST. In this talk, I'd like to explain opaque and its.
For some reason, you have to stay in the box for some reason.
Or else.
Or else.
Okay. So in this
Chairs
talk,
have a eject button.
Explain opaque and its update. Next, please.
It might be recorded or from
next, please.
for the more
Yes.
audio or something. I don't know.
As you know, the PEG, the password-only key exchange, provides not only password-only authentication involving between the involving parties, but also generation of session keys, which can be used to generate the secure channels between the parties. And the PEG protocol doesn't rely on public infrastructure, because the only secret the PEG protocol is using is a password. So therefore, the users don't need to carry any security devices. So it is very convenient to users. The minimum security the PEG protocol should achieve is the security against the offline dictionary attacks, because the password is chosen from a small dictionary, and the offline dictionary attacks are very powerful because these attacks can be done offline and without interaction with the honest parties. And there are two inherent limitations in PEG protocols. The first is online dictionary attacks are always possible, but these attacks are controllable because the servers can set a threshold dealing with the number of failed login attempts. The second is that server compromise always leads to password compromise. The next, please. And PEG protocols can be classified into balanced PEG and augmented PEG. As I said earlier, these PEG protocols should be secure against the offline dictionary attacks. The augmented PEG provides extra protection for server compromise. This is sometimes called the resistance to server compromise. There are many examples of augmented PEG: the AEKE, OSA, BBKE, BSBK, and also the AMP and SRP and OPEG. The OPEG belongs to augmented PEG. Next, please. This shows the difference between balanced PEG and augmented PEG. And here you assume that password user U, just remember her password small w, and server S stores the password verifier in its database. And the password verifier is a value, the output of the 1A function with the password w as its input. And now the server has compromised, then an attacker obtains the password verifier. In the balanced PEG, the attacker who gets the password verifier can impersonate the user successfully with the server. Actually, this attack doesn't require the offline dictionary attacks on the password verifier. However, in the augmented PEG, the attacker cannot impersonate the user with a password verifier. The only way for the attacker to impersonate the user is to perform offline dictionary attacks on the password verifier. Next, please. Yes, the OPEG protocol is secure against passive attacks, active attacks, offline dictionary attacks. It also provides a resistance to server compromise, and the OPEG protocol is probably secure in the random walk model. Actually, it requires a little bit strong computational assumption. And the OPEG protocol is highly efficient compared to the plain DPMR key exchange. The OPEG just requires to model exponentiation on the user side and 2.17 model exponentiation on the server side, respectively. After excluding pre-computable cost, the model expansion on the user side leads to 1, and the model expansion on the server side leads to 1.70. Also, the OPEC isn't the most efficient of SRP. Next, please. And as a feature of OPEC, it can be implemented over any cryptography security groups. Actually, the OPEC doesn't require any full-domain hash and ideal cipher in its construction. And also, the OPEC can be used as a relatively license. And if you're interested, you can see the IP disclosure. The OPEC can be easily converted to a balanced one by string off with some functionalities that was used to provide resistance to sub-compromise. Next, please. Next, please. Yes. From the 01 ID, we added an elliptical version of OPEC. These are the domain parameters that generally used, and in the parameter we set the cofactor k to be 2 to the n times q1 times q2 times qt, where the n can be 0, 1, 2, or 3, and every branch qi is greater than the order q for all I. Optionally, we also can set k to be 2 to the n. By using this cofactor k, the OPEC protocol of the elliptical groups can be more efficient in terms of the order check of the values. Next, please. This is the elliptical version of OPEC. In terms of the checking of values, large S and Y. Here, after receiving the large S from user U, server doesn't need to check the order of large S. The server just checks if large S is not on a point on elliptical E, or 2 to the n times x is equal to the point at infinity. It's the same as for the large Y on the user side. The other parts of the elliptical version of the OPEC can be just rewritten from the finite field version of the OPEC. And that's please. Yeah, that's all. Yeah. Thank you.
Hi, Shanaри, Chanley, and Jabber. Bitwise Shift Left had mentioned, is there a security proof of OPEC more recent than the 2010?
Yes.
The answer is yes?
Yes, the ePrint version is in 2010.
What was the answer?
Oh. Proof then 2010. The question and the answer, I think, is no.
Adam Langley, Google. So I must admit I followed that poorly, I'm afraid. But it seemed that you had lots of requirements on your EC groups, requirements around the cofactor, perhaps even requirements on the curve shape. I think one of the pertinent points for this group is what's the advantage of this over something like SPAKE2, which we also have a draft for, where SPAKE2 will work on, say the groups that we are currently specifying in the curves draft.
Yes, the advantage of OPEC over SPAKE2 is that it provides resistance to sub-compromise. It is an augmented PEG. The SPAKE2
I see.
is
Okay. Right. Thank you.
Yes.
So to clarify, the person in the Jabber room said that he thinks the 2010 proof is incorrect. So I don't think this is something we can discuss today, but I would encourage both of you to have this discussion on the mailing list.
Big shift left. Big wide shift left. Mike Hamburg. Okay.
Okay. One quick question.
Quick computational question, René. Can you go back to your slide where you had the computations going on?
This one?
Yes. On the left you have the computation of the value z or z. Do you think you would be able to get rid of this inversion on that side?
Sorry?
I suppose you can tweak the scheme so that you can get rid of this inversion on the left-hand side to compute the value z.
This one?
No. Yeah, you could. Yeah, exactly where you point, right? You think that you could tweak the scheme in such a way that you would be able to do the computation without an inversion there?
Without inversion?
Yeah. It's not this scheme, of course, but
yes.
Are you able to morph it into something without this inversion?
I think it is possible, but here we don't care about the possibility of this computation of z and with or without the inversion. Actually, we just care about the computation cost of the multiplications, but it is just a computation of the module the order q, but the actual the heavy computation cost in this protocol is g times y and y times z. So.
Okay, thanks.
Okay, so the final presentation. Wait, actually, what time is it? Okay, that's good.
Good afternoon. My name is Fu Liu from China Mobile. I would like to talk today about the SIP authentication use elliptical cover SRP5 protocol. Next. Everybody knows SIP is a popular standard security protocol for voice IP. It has been widely used in the wired networks, wireless networks.
Sorry, can you hold the mic slightly further?
Okay, sorry.
It's a bit loud.
SIP applies HTTP GGS authentication protocol for user authentication. Next. First of all, we talk like what is HTTP GGS authentications. This protocol is very simple. Client first send a query to the server, want to access a web page which require the authentications. The server challenges the client with a message including the real nonce algorithms. The client hashed messages including username, real password, algorithm, digits UI. Send back this response to the server. Server then compute this hash and compare the response. If it is success, the client can access the authorized web pages. In these schemes, the password is not transmitted in clear text. Is the transmitted in the hashed formats. Attack can get not the password directly, but can get the hashed password messages. So how they attack to break this game? This is very simple. attack can record all the transactions between the client and the servers, and use the following formulas to compute, and use a guessed password to compute and hash messages and compare the response. If this is the equal, this means he get the right password. Please next. Why this is the break can be break? The reason is due to the feature of the password. Usually password is very short, used in the practice. Most is the next 8 characters. More seriously, the password is selected by user's select. Its secret strength is about only 30 bit. So it can be break only used in the 16 minutes to get the right password. Please, this. Okay, this slide shows the safe authentication use the HTTP-based scams. This from this slide we can see the safe authentication procedure is almost the same as the HTTP-based audio. So the password offline decryption attack is also possible in the safe authentication scam. Please next. So as this in this forms is also is a very simple attack scams. Please next. How to address this problem? Actually, in 2009, IEEE have released a standard to address this problem, use a stronger password authentication protocols. The many protocols, when they review this standard, they are divided into 2 kind of the protocols. One is the balanced password authentication protocols. The other is augment password authentication protocols. But the first one is suited for the peer-to-peer communications. The representative is the PAC, which has been documented in RFC 4683 as a standard. The other augment password authentication protocol, the representative is the SARP, which has been specified in the RFC 2945. Next. ECSRP5 protocol is the ECC variant of the SIP protocol. It also defined in IEEE is standard. We apply the SRP5 protocol for the safe authentication, not use the SRP protocol because it uses ECC crypto. ECC used is much efficient the SRP protocol. The basic idea of the ECSRP protocol is that the password is integrated into the temporary EC public key. So if an attack want to get the password, the attack had to address the ECDAP problem. But next. For the system installation, password verify first is computed as follows. Is a hash messenger such as the SAT, SIP, UI, password, indexed. This hash values is as a password provider key on to compute a pointer on the init covers. After that, the server just stored the following information in the database for each user. CPUI, start S, init cover, index, password, and verify. Put it next. Now look at the procedure safe authentication using the init cover ECSR P5. The client first start an initial request, use messenger SIP, use his SIP URI. The server makes a looks up according to the SIP URI, get the password verify, start ECAI. After that, generate the password integrated public key WS. And the response to the client with start ECI WS. With this messenger, the client can compute client first generate a public key WC and compute the shared secret Z, and continue, he can compute the confirmation value to prove he can know the password. On the send, this is another request to the server WC on the CC. The computer, the client server, they use the client's public key WC and his private key computer the shared secret Z. After that, he verifies the value CC on the computer the confirmation CS. If the server if the verified is successful, the server can be sure that the client have known the password. After that, he send the confirmation CS to the client. Client verifies the value CS, and if it is successful, the client can assure that he knows the server knows the password verifies. Please. We certainly take and look at the security considerations. First, this protocol could show against the offline dictionary attacks. The reason is that the information messages exchanged between client and server, which including the password message information is the password integrated public WS. From this information, from these messages, the attack could not get the password. This because this password-related element events is shadowed by the ID endpoint TSG. The offline dictionary attack is shown against the very simple is usually blocks the user authentications when the terms authentication field reach the default value and set it in advance. Please next. Now, man in the middle attack. This is the is impossible because in the client side, on the server side, there are make a verification to the confirmation venue CS on the CC. For the replay attack, because for each sections, the client on the server generated the new public key on the provided keys. So each authentication session have its unique shared secret. So the client can detect the replay attack by compare the CS with the expected confirmer value CS. On the server can also detect the replay attack, compare the CS with its expected confirmation values. Please next. In this protocol, we had to use some inimical covers. We simply take some covers from the seeker registered cover, suggested covers. Also, this covers also is the recommended by NIST. So we do not make many research on this point. Okay, please next. Okay, please next. Okay, for instance, there are some open issues. First, we should make an thorough analysis of the security of this protocol. Although this protocol has been standardized in IEEE, we do not know whether they exist security flaw or not. We cannot know. The other thing is the performance. We also do not know which covers is much more efficient when used the inbuilt covers. The third question is we have used the covers suggested by SIG, also recommended by NIST. These covers are still secure or not? Okay, this is all. Thanks.
Okay, so you're basically asked about feedback on whether what you're using is secure and just general help with this, how to use this.
Yeah, how to project the tool. Okay. Because this is a fundamental problem.
Okay.
Yeah.
Any comments, questions?
Kenny Patterson. Is it true that you could take your specific protocol based on SRP5 and replace it with any PAKE and still solve the problem?
Yeah, we use this protocol to adapt to the SIP application authentication procedures.
Okay.
Because the SIP, because the ECSRP5 is a generic protocol on the message exchanger is not looks like this. So adapt the message exchanger to the SIP procedure because the SIP is the fact. We cannot change the SIP authentication procedures.
So any PAKE protocol that has the same flow of messages as this PAKE could be used in place?
Maybe.
Okay.
But I cannot sure. Maybe. When we use the ECSRP protocol, we actually have two reasons. First, this protocol is actually efficient and also standard, also is recognized in the IEEE. The other thing is this protocol, we have not found any patent-related NIST protocol.
Thank you.
Okay.
Okay. To Chair's surprise, we're 15 minutes early. Any other topics? Any other business? We reserve the right to, cut discussions short as usual, but...
I just wanted to say that I think I've solved the problem that Kenny said was impossible to start with.
Is that preventing you from saying anything in CFRG?
Yeah,
Is that,
the H7 generation one.
Okay, good.
Okay. Well, thank you for attending.
Blood on the floor.
Right.
I want to know that HSM or whatever. So what I'm going to do is, what is the so the guy about XMS?
Sorry.
You Andrew?
But he's
Oh, hi.
thank you.
Nice to meet you. I'll talk to you in a minute. So, can I give you some feedback?
Yeah, we actually did that.
So, this is